Okay, welcome to video number 7 in module 6 traffic assignment, and here we're going to talk about iterative method of traffic assignment. Okay, so far you studied 3 methods: all or nothing. All or nothing usually I would like to call good for nothing maybe. All or nothing is basically if you have a shortest path, assign shortest path between two zones, assign all the traffic between the two zones onto the shortest path and nothing to the other paths. That's why it's not realistic, and that's why it's good for nothing. Actually, it's not true, it's not good for nothing, because all or nothing becomes a part of the assignment or a part of the process in the other assignment methods. Like incremental, when you did, for each iteration you're doing actually all or nothing. So the other one is stochastic. Stochastic has its own problem. You assign it to multiple paths, let's say 3 paths. First of all, how do you identify 3 paths? The algorithm we mentioned, it's only going to give you one path, which is the shortest path. And if you have 3 different paths, 14 minutes, 15 minutes, and 16 minutes each travel time, it is only going to give you the 14-minute travel time path. Other two, it's not going to give. So you have to get fancier and create better algorithms to give you the other 2 paths. And now, why only 2 paths? Why not 2 more paths? Why not 5 more paths? So where does it end, and how do you find out the probabilities associated with those paths? If you use the logit model structure, how do you come out with the utilities associated with each path? So it is getting complex, more complex. Stochastic on the incremental on the other hand, we used for incremental 40, 30, 20, 10 in iteration 1, 2, 3, and 4. Who says that is the right way? Why not 2, 10, 30, 40? Or even drastically, why not 35, 30, 25, 10? So you get the picture. So that is kind of even incremental doesn't sound very right. There is no accurate way to predict paths taken between by trip makers. All or nothing is not the right way to go about. So the philosophy here is do it for X number of iterations, take the average at the end of all the iterations. That's the philosophy in iterative assignment. Here's the pseudocode. Let's say we do it for 4 iterations. That's typically what you do for an iterative assignment. You loop over all origins. If you have z number of zones, you increment it zone by zone from 1 to z, and for each origin zone find the shortest path, and once you shortest path tree, once you found the tree, loop over all the destinations from the origin, from this origin to all the destinations, rebuild the path, and in the links along that path add this traffic between O and D, and do the same for the next destination zone. And this is the loop. If you are familiar with pseudocode, this is how it looks. Yeah, the pseudocode. Actually, this is not really pseudocode. I try to make it look a little bit more interesting by using phrases like, next iteration, please. So anyway, it will become much clearer after we finish a problem. So we may revisit this slide later. So let's take the same example we solved for iterative assignment. Exactly the same thing. There's nothing, but you're using a different method. Once again, A to B, trips 30. Capacity 30 in all links. Travel time 7, 10, 16 by links L1, L2, L3, and same BPR function holds good, and 100 trips between A and B. So this is the this is the setup for iteration 1. The network you see here is not yet loaded. So this is where you start. This is what you see are the free flow travel time. See, even though all or nothing assignment by itself is not used as the holistic assignment method, but all or nothing plays a major role in every method that uses iterations. It plays a role in iterative assignment, as we are going to see now. It played a role in incremental assignment, and it will play a role in equilibrium assignment, which we are going to study later. Now, what we do have is 100 trips from A to B. So first you start with your iteration and find the shortest path, which is this guy, and assign all 100 to him. So that is going to change your, so that will make the travel times here 0 on link 2 and link 3. Once you assign 100 to link 1, your travel time changes to, so that will work out to 136.6. 136.6. By the way, this is for link L1. Shortest path now is link L1. You assign all that to L1, and the travel time on L2 is not going to change because the free flow travel time is 10 and it has 0 volume. It will remain as 10. The same goes with link L3, which is going to remain as 16. So this is the state of your network at the end of iteration. So you have these volumes, and what you see on the right hand side are your travel times. So let me strike this out, and 136 is your 136.6 as your travel time. Let's go on to the next iteration. Yeah, I forgot to put the mark here. Here 136.6 is the travel time at the end of previous iteration. Now if you look at the shortest path is going to be L2, and you assign all 100 trips to that one and 0 trips here and 0 trips here. So now here is the problem. Now you have free flow travel time on link 1 is 7, and now that volume is 0 here. You get back to from 136 to 7. It switched back to 136 to 7 again, because there is a 0 traffic. On this one, on the other hand, it changed to 100, and the value comes out to be 195.2. 195.2. And because this guy has 0, the travel time, free flow travel time is 16 and 0 volume, and that will become 16, and this is for link 3, this is for link 2. Sorry, I didn't put it earlier. Now the network state at the end of this is this travel time becomes 195.2. So as you enter the next iteration, you have 196.2 is your travel time. Now who's back in play now? This swung back to 7 minutes because you didn't put any volume last time. So that guy is back in play, and this time the shortest path is L1, and you put all 100 there, and the beat goes on 7, 100, and that will give you again 136.6. So you will change this to 136.6, and because this time you have 0 and 10 minutes, you'll swing back to 10 minutes You'll swing back to 10 minutes and 0 volume, 0 volume. So this will remain, L3 will be, see, this is L2. This will remain as 0. So this is how the network looks at the end of iteration 3. So we have to take back this state. So 100 trips on this, 100 trips on this, and 0, 0, and the travel time here, 0 on L2, 0 on L3, with travel time 10 and 16 again, whereas 136 on link 1. Okay, the state we left iteration 3 is not exactly this. There was a travel time of, I believe, iteration 3, yeah, here we have 136.6. So this is the state, as you see on the screen now, is the state you left iteration 3. In this travel time state, the shortest path is on L2, so we will assign all 100 here. So let's do for L2 travel time again. You don't need to do it because at the end of iteration 4 we are going to stop, but for completion's sake we will do this. This again comes to 195.2. Now, since all 100 are assigned on L2, you get 0 on L1, 0 on L3. So 0 here, 0 here, 7 and 16. You get 7 and 16 for L3, and this is L1. So 4 iterations are done. One way to summarize all the maneuvers we have done is I was trying to explain how this is done, but who's keeping track? Well, the assignment program does. I put it in a spreadsheet to keep that from iteration to iteration to show you how this thing is done. Iteration 1, you started with free flow travel time. So you pick the shortest path, assigned all 100, updated the time. You went into iteration 2 with these 3 travel times, and you pick the shortest one, which is 10. You assigned all 100 to them, updated the travel time, updated the travel time, updated the travel time. Again, this is the contender as the shortest path, assigned all 100, updated the time, and the beat goes on. If you look at it, at the end, you sum all the all or nothing assignments between each iterations. By the way, all or nothing is part of every method that uses iterations. Okay? So when you sum it all up, you got on link 1 200 vehicles, on link 2 200 vehicles. And what the method says is, if you do for 4 iterations, you divide that by 4, and you get 50 on link 1, 50 on link 2. Now, for link 1, you want to get the final travel time, which is you have 50 vehicles here on a 7-minute, oops, I didn't do it right, on a 7-minute free flow travel time, and you get 15.1. That's how the travel time on link 1 will be, 15.1. So you got 50 on link 2. So this is your link 2. Traffic is 50 and its free flow travel time is 10. And if you evaluate this term, you get 21.6. So the travel time on link 2 will be 21.6, and travel time on link 1 is 15.1, traffic on link 1 is 50 and traffic on link 2 is 50. So this value here is what you are putting in there. Of course, this is an orphan link again, you get 0 volume and its travel time remains at 60. So even after 4 iterations, the third link L3 did not pick up any traffic. So bigger picture, the fully loaded network looks like this. So everything I scribbled earlier is what is written here. So final solution is volume is that on link 1 50, link 2 50, link 3 0, and travel times are computed like this. This is a tabular form of reporting, and this is a map representation of the traffic volumes. You can use the thickness of the line to depict the actual volume or a color, whatever. You may think it's almost reasonable, isn't it? Now, there is a big problem here. See, from start, which is iteration 0, to iteration 1, there is a huge swing in travel time from 7 to 136. It never happens. That much of a huge swing is not going to happen in reality or ever. And again, from iteration 1 to iteration 2 on link 2, the travel time went up from 10 minutes to 195.1. Huge swing again. And not only that, they swung back again high and low. So those kind of swings are not realistic in practical, or say not realistic. So what we do to prevent these kind of huge swings is use what's called a damping method. So they make these swings less dramatic. What you do is, if you are trying to go, what is the travel time that you're going to use for next iteration will be, you pick up the travel time of the previous iteration. First of all, use a damping factor. So let's say x, which has a value between 0 to 1. Usually you use 0.25 as your damping factor. So coming back to this, your travel time to be used for the next iteration is going to be travel time from previous iteration. In other words, you are in iteration number 2, so the previous iteration is 1 times 1 minus x. If you use 0.25, it will be 1 minus x is going to be 0.75. T computed after this iteration is number 2, right? So whatever t you computed, you only use 25% of that, which is if you use 0.25, of course. So that is how the damping works. As anything, if we use a problem, it will become much clearer. Again, the same problem, one line is added. Use 75-25 damping. That's what we are going to do. Everything the same. Capacity is 30, trips are 100, etc. Now, these BPR functions look different, right? No, travel time estimation functions look different. So this is the damping formula which we sought out earlier. So take, in this particular case, when you started iteration 1, these are your travel times because there is no load on the network yet. First pick the shortest path and put all 100 guys on there. So we will put 100 there, and its travel time is 7. You update it, and this segment here is the travel time computation. We are going to use only 25% of the new computed travel time and 75% of the previous travel time, which is 7. And if you work this out, this value will come out to 39.4. That's what your travel time going to be? And how about these links? Not much has changed, and therefore it is not even this is link 2, this is for link 1, the shortest path is link 1. So this is going to remain as 10 and this is going to remain as 16 because there's no traffic on them yet. So we entered iteration 2 with the travel time on link 1 updated to 39.41. 39.41. So 39.41. And here we have, by the way, we are not accumulating the traffic at all. Unlike in iterative, unlike in incremental, where we keep adding traffic from previous iteration, we don't. Each time we are treating it as an independent all or nothing assignment. For each iteration, we are treating it as an independent iterative assignment. So we are not accumulating. We may be accumulating in the background as a counter, but for assignment purposes, independent all or nothing assignment only. So the shortest path after this, after previous iteration, now is going to be L2 with the travel time of 10. So let's do link 1 travel time is going to be, so earlier we had 39.41, right? 39.4 is the from the previous iteration, and you have a 0 and travel time times 7 times this value will come out to, I am looking at my spreadsheet here, so that will come out to 31.31. 31.3. So what happened on link 2 is different. You have this as the shortest and therefore you put all 100 there, 0 there, 0 there, and 100 here and 10 here, and the previous travel time is 10% of 75% of 10 plus 25% of this whole expression. That will give you a travel time for this particular link as 56.3. Since the third link L3 didn't get any traffic, it will remain its travel time as 16. So we are leaving iteration 2 with a travel time of 39.31, 31.3 on link 1 and 56.3 on link 2. So this is how you start iteration 3 in this state, 31.3 and 56.3. So we entered the network, we entered iteration. So we entered iteration 3 with 31.3 travel time on this link, 31.3, and 56.3 on this link. So that's what we have. Now if we want to, not want to, we identify your shortest path is going to be like this. This is the shortest path, which is L3, which is where all your 100 trips grow. So this is your all or nothing assignment during iteration 3. Now back to updating the travel times again. 0.75 times for link 1, it will be 0.75 times 31.3, and 0.25 times 7 times here it is 0, and that will come out to 25.2. And at the end of this, you will have on link 3, you will have 56.3 times 0.25 times 10, and the volume in this iteration you have 0. The new travel time on link L3 is the expression is going to be 75% of 16 plus 25% of the newly computed travel time with the expression as you're just seeing here. So you assigned all 100 to L3, and the values are going to be here you have, oops, same problem again. Here you have 44.7 for link 2, 44.7. Geez, this is link 2, sorry folks. 44.7, and I don't have, okay, the link number 3 comes to 90.1. 90.1. So if you want to update these travel times, at the end of iteration 3 you got 25.2, 25.2, and 44.7, 44.7, and 90.1, 90.1. So this is the input travel times. These are the input travel times for iteration 4. So we entered iteration 4 with these travel times. Obviously now the shortest distance between A and B is via L1, and we're going to assign all this time I use different color for the iteration 4 operations. So that's your shortest path, which is essentially L1, and we're going to assign all 100 trips there. So we are actually at this point you can stop. At this point you can stop because assigning at the end of iteration 4 is where you stop, and then you take the averages, and then there is another step you need to do. Can stop here, can stop here, because there is no point in updating travel times unless you want to conduct another iteration. So that's the reason why we are stopping. Now go back, look at your bookkeeper. Bookkeeper is all the counters you set in the computer while you are doing this kind of assignment. I use spreadsheet to show you this problem. So we have, I set it up in a large spreadsheet like this. I have capacity value, T sub 0, alpha, beta, which are of course the functions of BPR, the parameters of BPR function, and what we started with in iteration 0 and how the travel times keep changing. So once the end of this iteration, what you're going to do is sum these up. This is the traffic volume in iteration 1, iteration 2 is 0, iteration 3 is 0, and iteration 4 is 100. So if you sum it all up, you get to 200. Same thing, you sum these values for each link. And then you take an average. So average of 200 over 4 iterations is 50. Average of 100 over 4 iterations is 25, 25. So this should add up to your total trip table from A to B. And now that you have assigned the volume and taken the average, now compute the final link travel times. For L1, you have 7 times this expression times 50 divided by 30. Same thing for L2. Same thing for L2 here. You will use, of course, 10 is the free flow travel time on L2. 25 is the volume, and L3 16, again 25 is the volume. And if you compute these things, you will get 15.10, 10.72, 15.1, this is 10.72, and 17.16, 17.16. So we are done, but let's clean it up. So you can strike these off and then put it as 15.1, 10.72. Is that right? Did I get it right? 25. Yeah, that's correct. And here you get 17.16. Now we take a good look at the pseudocode. I'm just going to leave it to you to absorb it. So it kind of makes sense. Right here, update link travel time in this link performance and all or nothing function. So in the damping method, using damping, use damping here. So take a good look at this pseudocode and it will all make sense about the iterative assignment. So take a good moment to look at the final assignments using each method. The very first one we did was all or nothing. Everything went on this route and nothing on this. But that jacked up the travel time on link 1 to 136. And we said, wait a minute, that's not going to be right. And then we went to incremental. We used 40, 30, 20, 10 in iteration 1, 2, 3, and 4. And in the end, you ended up with 60 on L1, 40 on L2, with a travel time of almost 24 and almost 47 on those links. And we said, 40, 30, 20, 10, or whatever the split is, that doesn't seem to have any real good justification. We went with the iterative method where we'll do for certain number of iterations and take the average. That made you saw a huge swing in travel times from iteration to iteration, and I thought maybe there should be a better way. So we settled on, or we came to iterative with damping. This method gave you 15.1, 10.7, 17.6. Only one method put some volume on link 3, which is the iterative method with damping. We are on to something with this. So this had been a popular method until computers got little better and the methods for equilibrium assignments have become much smarter and smarter. So the next is going to be on equilibrium assignment, which is more popularly used. Another setup here is look at the travel times. Who in the right mind will travel by a link that really has 136 minutes when the competing ones are 10 minutes or 16 minutes? So out, that guy is out. Even here the disparity in travel times is pretty high. Here too the disparity is high, but look at this. These things, I mean, in terms of difference from each other, they are not that different. So the variation is less. You will see in the next one, equilibrium assignment, they are going to be equal. That is going to be in the next video. And this marks the conclusion of video number 7 of module number 6. See you later.